Thank you, everyone who's called in. We'll have a few more people trickling in, I'm sure, over the next few minutes, but we're going to get started. Thank you. Today, our webinar is about covariate effects using forest plots. So the title is Evaluation of Covariate Effects Using Forest Plots, an Introduction to the coveffectsplot R package. So if you haven't been to one of our webinars before, the SXP is a special interest group that's joint between ASA and ISOP. We would like everyone to join. We have a lot of good resources there. It's free to sign up. You don't need to be a member of any professional society, even though we are chartered by both. Membership is not required. So this QR code takes you directly to the sign up page. We only send out emails maybe once a month on average with some updates or other information. I think this is a really good resource. Most people who checked out and perused our website feel that they've really found it a good resource for a lot of the work they're doing. So please sign up. We do have a couple updates. We just had an election through back in February, and we did have the end results. So we had 4 new members to our steering committee. 2 of them, the top 2, are our pharmacometrics steering committee members. So I'd like to welcome Yuan Xiang from Janssen and Subik Bhattacharya from Astellas, and then our ASA representatives. The statistical representation of our new steering committee members is Marion Korhui and Yi Zhang. So I want to thank them, and are excited to start working with them for the next 3 years. I guess this slide should have been earlier, but what is SXP? So it's Statistics and Pharmacometrics Special Interest Group. We know that today's modeling informed drug development world, there's a lot of potential for statistics and pharmacometrics to work together, because frankly, this is the future of drug development, and it's an exciting future ahead for both of us. So we're working to bridge the gap between both of us and hopefully, improve drug development, and we definitely want to have everyone getting involved and work together on this. So especially thank you for calling in, and please join if you haven't. So with that, I want to get to our speaker. So our speaker today is Samer Mouksassi. He's from Certara. So Samer has worked with Farsight Certara since 2007, covering statistics, NCA, pharmacometrics, global public health, real-world data, and model-based meta-analysis. His current role at Certara is Senior Director, Africa Region Lead, involves mentoring and building new pharmacometrics teams in Cairo and Cape Town with the goal to create a sustainable ecosystem for pharmacometrics in Africa, where modeling and simulation quantitative methods are used to optimize drug development decisions. He has a passion for teaching and for building tools that empower non-coders to communicate effectively and efficiently. He's the author of the coveffectsplot, GG Quick EDA, and Tidy VPC-R packages. So with that, I'd like to thank Samer, and I'll pass the slides over to him.
Thanks. Welcome, everyone. I will now share my screen. Good. So I hope you can hear me well and see my screen. So as mentioned, today I'll be presenting to you one of my papers that we published last year. Basically, it was a CPT-PSP tutorial showing how you can use my package coveffectsplot and how you can produce covariate effects. First, I would like to mention my co-authors, J.F. Maria and Nathan Tusser, who wrote the paper with me. Also, other colleagues like James Craig, Dean Atali, and Benjamin Rich, who helped me in developing this package, wrote part of the Shiny app, or wrote some functions that are now part of the package. And today's focus will be on coveffectsplot, which is part of our open source GitHub collection of tools that you can find on that link. So today I will be guiding you on first, I will try to define what are effects plot as we apply them in pharmacometrics. I will show how we can generate via simulations the effects of our covariates, including uncertainty between subject variability, etc. There is multiple ways and methods. And by the end of this talk, you will get started with coveffectsplot, and hopefully you can start using it to communicate your covariate models for the models you are building. So first, I would like to, 1 second here, I'm not sure why this tool, yeah, that's cool. So first, because I know maybe we have some non-pharmacometrician or statistician, etc. So very quickly, pharmacometrics model, in pharmacometrics, we model concentration, PK concentration data, for example, where we are modeling PK. So we have multiple data points coming from same subject. So it is a longitudinal type of data. And here I'm showing PK profile over time. And just I'm using example where I have a population where I have extensive metabolizer, poor metabolizer. Of course, we have body weight. And for sake of illustration, I divided my patient population into healthy and patient. So we take this data and we build a nonlinear mixed effects model. Here I'm showing a PK model, one compartment model. But basically, we try to describe the curve using a nonlinear mixed effect model. And our pharmacometrics models are parameterized. Say you can hear we have clearance, volume, absorption constant, and typically covariates that we use impact model parameters. So we model concentration, but the covariate won't be affecting concentration. It will be affecting the parameter like clearance, volume. That's to be aware of, especially when you are used to like statistical models where covariate directly impact your dependent variable. And part of these parameters, for example, clearance, you might see in most models we use a multiplicative form of covariate. So it's population clearance times a covariate body weight standardized over the median value or a reference value of choice to a power of something. And then we can add categorical covariate and a random effect. So our models most of the time don't have interaction. So they become additive on log scale. So this model here will, if you take log on both ends, will become perfectly simple and linear model. Okay, so what are effects? And that's, I would say, common in statistics. And I will show example how to generate effects in R before going into a pharmacometrics application. So given the model equation, we want to compute marginal effects. And marginal can mean something different depending on field, depending on model, but you will see later in this talk what I mean. So the marginal effects at the representative values of this covariate. By representative, we might want or think the median of body weight would represent, or maybe the 25th percentile, 71st percentile, and so on. So we compute the effects at representative value from the statistical model. So, and here we call it covariate in pharmacometrics. Sometimes we call it predictors in some fields or features in machine learning. So it's just predictors we used in our model. And how do we generate this effect? We conduct prediction / simulation because sometimes we involve random effect. But yeah, basically we are plugging in values in the equation of the model. And the standard approach would be that we vary one variable at a time. So basically, I'm just trying to get my pointer here. So we vary, say, I want to study the effect of body weight. So I vary, I may choose body weight equal 50 kilo, 60, 70, 80. So I want to see what are the impact of body weight on clearance or on AUC. But I need to, in my equation, to plug in values for my other covariate. So typically we hold the other variable constant by using the reference value. So one can also compute the effect for combination of covariates. Say, oh, what happened when weight equals 50 and EM equals 0 or 1, so on. But then the question, will it be representative of the population? So as I mentioned earlier, in pharmacometrics, we can compute effect on clearance on volume, but clinically, it's more interesting to study the impact on exposures, say AUC or Cmax or Cmin. So we want to illustrate the effect not on parameter of the model, but on derived ones like AUC and Cmax. And to do so, we want to include the uncertainty. So when you fit a model, you get a parameter estimate, but you also get a standard error on it. You get a variance covariance matrix. So we want to use this information to illustrate our uncertainty. I'll show you how we do it. So here in this equation, I have parameters in blue, covariate in green, and random effect in red. And this will continue this presentation, these color codes. And sometimes it's of interest to contrast the covariate effect versus unexplained random effect. I'll show later. That's a figure taken from my CPT-PSP tutorial. Basically, it's just a toy simulation where I simulate, okay, what if my uncertainty, I have 10% error on my, here I'm using clearance of 4. So I'm showing, okay, what is the distribution of clearance when I have 10% SD, and then you see here I'm plugging in a weight distribution, computing the interval, okay, and then I'm adding a between subject variability of 30%, and then below here I'm comparing. Okay, we can see the uncertainty is smaller than the covariate, which is smaller than the effect of the BSV, and it is interesting to standardize. So here we have 4 to 6, but when we normalize, so everything becomes 1, we now go into a percent. So basically, oh, I'm 50% higher. So do I need to change the dose or something? So you'll see I use standardization in my forest plot later down the road. So I will be sharing a script. Basically, that shows that in R, when you fit a model, say I use Harold-Verse family of packages like regression modeling strategies, RMS or HMIS. And the advantage is once you fit a OLS, ordinary square model, so I'm showing here that I got like the coefficient for my weight and covariate. And in R, you can just summarize the model and plot the model, and boom, you have a forest plot showing the impact or the effect of weight on here. I made a shortcut, so I'm not modeling concentration. I'm using simple model on AUC normalized by dose. So you can see here, okay, what is the effect of body weight? By default, RMS would use, okay, what's the 75th percentile to the 25th percentile, because we think it's representative of the data. So, and for the categorical covariate, we have EM over reference, so poor metabolized versus reference. We see here's the effect, and health over patient. So, and you will see in the code that I'm sharing same model, I can predict and compute different type of effect. So you will have codes that help you reproduce these plots. But the question we are dealing with, okay, that's in R stats. how can we bring something similar to our pharmacometrics model? So a few years back, we got this publication from FDA team, and then basically recommending, oh, it's cool to have forest plot. It's a concise visual presentations that can be suitable to be plugged in drug label to make decision about dose adjustment or not. So here we are illustrating the effect, say, of concomitant medication on Cmax and AUC using a folded change point interval type of data. So that was pretty cool. But what we didn't have an answer in this is, okay, what if we have a continuous covariate like body weight? How should we split it or represent it? What if we don't have, say, a DDI and NCA study, but we have a POP-PK model? And recently, the guidance from FDA on population pharmacokinetics was updated. By this, I mean last year we had the guidance that was the same for like 10 years, and then we had an update, and now we have forest plot mentioned in the guidance. So here it's a zoom of this page. So basically, in this guidance we have multiple mention of type of simulation we can be doing to illustrate our models. So today I'll focus on like paragraph 2 and 3, because that's these are recommended to illustrate the effect of covariate. So we use uncertainty. It depends on our objective, but today I'm focusing really on communicating our covariate effects. And again, the FDA recommends that we use AUC, not clearance or volume, and we incorporate uncertainty to study the relative importance of covariate on exposure. So that's a univariate approach that you'll see later on. Also, this approach is recommended when we are trying to find dosing regimen for testing in future trials. So simulation with uncertainty on parameter is what we need to illustrate the relative importance of covariate and to design new dosing regimen. Also in this guidance, there is another type of simulation where we incorporate between subject variability, and that's important when we want to study the range of individual prediction. It's okay, what kind of AUC values I might have in my population of subject. So I incorporate BHV. And when we want to understand the range of individual prediction, we no longer want to vary one covariate at a time. It's no longer realistic. What we want to plug into the simulation is realistic demographic distribution. So there's many ways you can build the models that simulate correlated covariate, or you can resample from a database that of patients that you have already. So you keep all patient data correlated together. So you sample one patient, we will have weight, age, albumin, etc., that are all, and that preserves the correlation. So simulation with uncertainty BSV and realistic distribution is used when we want to illustrate the range of individual prediction. So I've been using like ancestor of coveffects if you want. When I use it for this summary basis of approval, it was not even a package. It was, but yeah, I've been using it for, you can find many like approvals or some base approvals at the website with this type of visual and simulations that I'll be illustrating today. And more recently, I've had a client getting FDA communication. Like I got this maybe 2 weeks ago from one of my clients, and so he got, the applicant is asked to present univariate, multivariate assessment of statistically significant covariate on exposure metrics, CTRAF, Cmax, AUC, and present this simulation as a forest plot. So now the agency is requesting this type of visual. It's becoming like routine POP-PK work, if you will. Back to the Menon-Anderson appendix. So that's, remember, that's a paper that first recommended to use forest plots. So just to illustrate, so here I'm like, if you want to read this table, and I'll give you maybe 1 or 2 minutes. So how long will it take for you to understand this table? And to help you, I'll be asking 2 questions for you to try to see. So my question to you is, which concomitant drug increase exposure the most? So here we have like a persistent drug label, and we have concomitant use of some like protease inhibitor or other antiretroviral. So, and second question, which one decreases exposure the most? And then are the effect consistent across Cmax, AUC, and Cmin? So I'll give you a few seconds, try to look at this table, try to see, try to find which concomitant drug has the biggest impact or effect. So without delaying things more, you realize that that's a tedious task. It requires a lot of reading, a lot of, okay, it's very tedious. What happens when I represent this data using a forest plot? Okay, same question. Which one decrease exposure the most or increase exposure the most, and are the effects consistent across exposure? So here you can see, okay, increase the most, boom, I have indinavir 1.4 on Cmin. So that's increasing Cmin the most, and it has less impact on AUC and Cmax. How about this guy? Okay, nevirapine. And yeah, it is impacting Cmax 1.4. So, and you can easily detect that lopinavir, ritonavir has like on the lower end, the biggest impact. So, and because we are quantitative, I also have this table. So you have the exact number, and of course you can play with the precision, so on. So I hope with this small demo exercise, I convince you that forest plot facilitates interpretation of clinical data and accelerate generating insights. Much quicker to look at a plot accompanied by number versus having pure text without any visual. And that's the main reason I wrote this package is, okay, I can generate these plots quite easily. So that's a Shiny app that comes with a package that writes the code for you. And so you learn how to write the code. So here, just exit PowerPoint, go to our studio. Basically, first, of course, if you don't have the package, you install it. It is on CRAN, and you can have the dev version on GitHub. So, and I have this particular data part of the package, so you can use it. So I'll show you. It all goes well. Now Zoom can compute. So you run this command and you get this plot. So I'm not sure why R is not working now. Okay, maybe it's just a OneDrive issue. But yeah, you can, you run this command and boom, you get this plot. And this is fully interactive. You can like change the order, you can exclude some of these values and so on and so forth. So, and the app, once it loads, you have a button that help you get the code. You have this show code button, you copy it, you use the data, and you can reproduce a plot and code. Also, in my as a help, I have many examples. For example, that's taken from the help. If you type help for a plot, it gives you the code. For example, here I'm showing AUC and Cmax split by molecule. Here I have a parent and metabolite type of data, but you can easily switch this visual to, oh, I want to head-to-head compare parent and metabolite and split AUC and Cmax into different panels. So, okay, now AUC and Cmax are in different columns while I am head-to-head comparing parent and metabolite. So it is using ggplot behind the scene, and it's any way you want to use facet or splits is compatible because it's a ggplot. Sometimes you might hear about, okay, tornado plot versus forest plot. So we have this figure in our supplemental material as a paper where we, I will get my pointer back. So we show that whether it's a tornado plot, which is a horizontal bar plot, if you want, or forest plot, it's exactly same data. It depends how you visually represent it. So basically, it's the exact same data shown differently. Typically, we don't show in the middle, like we only have a bar, like a min-max or 5 to 95 percentile. But here we show the exact same data. It doesn't guarantee that, oh, if it is a tornado plot, we use BSV or not, or uncertainty. You still have to tell the viewer how you generated these intervals. Did you use uncertainty, BSV, etc.? You need to describe how they were generated. And the way I designed my plots in this package is you can face it or split by parameter, so AUC, Cmax, 1 or more. On the left side, I have the covariate name, so weight. So I know, oh, these are the effect of body weight at 56, 72, etc. kilogram. And then so here it's a univariate case where I vary weight, holding albumin at reference, so on. So that's the effect of albumin when albumin changes from 40 to 50. That's the effect of 6 male as compared to my reference female. And you can see here, we need to take into account or take care of, okay, it's important to keep the direction. Okay, when I go up in the axis, my covariate increase all the time. So albumin is going up, weight is going up, but these two have opposite effect. When weight go up, my AUC go down, while my albumin go up, my AUC go up. So you have full control. Also very important to me is to have clear legend. So all my plots would give you a legend that, and you can edit the text quite easily. So you can describe at the text you need to tell, okay, what is this with reference area and a line, also with a numerical table on the side, because we want to exactly know what are these numbers. And you will see example later on, we can use color and shape. And if you write ggplot, you can use size. So minimum requirement to use coveffectsplot is to generate the effect. So we illustrate this in paper, we get covariate. So we generate, okay, the mid, the lower and upper, and the label is automatically done in the app, or you can generate it in code. Basically, it's just a formatted mid, lower, upper, where you define significant digits or a way to represent these numbers in a way that the text would make sense. But it's a big question, okay, how can we compute or generate the effects? So that will come next. So first step was, okay, so this package will help you generate these graphics quite easily. You can click a button using Shiny app to generate, but okay, how to generate this effect? So first, you will need a PK/PD model, of course. My workflow requires you to recode your model into R. R is super cool, super fast to do simulation. My vignettes use mrgsolve. I first learned mrgsolve, but you can do the same if you prefer PK/PD-SIM or RxODE2 or any other RSNLME and so on simulation package in R. And I also use the R package data table because when you simulate millions of profiles, you need efficient memory management. Data table is quite nice about that. So you recode your model into R, and then you decide, okay, what type of simulation am I doing? Of course, we always need fixed effects, but do I need uncertainty for covariate communication? Yes. Do I need to include BSV? Yes, no. And if you want to include uncertainty, in my vignette, I listed you can plug various covariance metrics, and you can plug in a bootstrap for results or stochastic SIR. So it is compatible. And next comes a question, okay, what kind of covariate I plug into my simulation? So first, we have varying one covariate at a time, or what I call covariate univariate, where you vary, say, weight, Helldig, albumin, and other at reference, versus the other method, which is covariate multivariate, where you plug in a distribution of covariate. So you preserve your correlation, and you can resample by patient from a database or by subject. Sometimes you want to extrapolate to a new population, or you plug in a real world data type of distribution. So yeah, that's also possible. Once we decided and we have all set up, we simulate enough replicates. So in my vignette, I use 200 to 500, but you will need to see if it is enough for your application. Then we compute parameters such as AUC and Cmax, compute intervals, and generate plots. So on purpose, coveffectsplot don't have functions that automate computation of parameter or interval, because each application is different. So I show examples on how this can be done and keep it open for the user to apply it the way they need in their particular application. So, and what's good about the field, more recently I've seen more R packages being developed or to generate forest plot of covariate effects. For example, a PM forest from our Metron colleague, or PMX forest from pharmacist colleague, NM project from AstraZeneca folks. And I'm sure I forgot or I didn't find some other solutions that are available. So it's becoming, we have more options to use, and it's becoming, again, standard to generate these forest plots. So that's my vignette, the first vignette called PK example. You have the source code, the RMD in a part of the package, and you have the HTML. But here it's just, so yeah. So we are in univariate case. So first application, I'm using fixed effects, uncertainty, but no BSV. So, well, first I simulate with BSV, then I turn it off, and I contrast what is the effect of covariate as compared to BSV. So first I write my mrgsolve model. So I have fixed effects, I have reference covariate values defined again as a parameter. I'm using built-in model to compartment with absorption. I have my parameter equation. So again, covariate affect parameter. I have albumin, sex, and weight affecting clearance, while sex and weight affecting volume, and peripheral volume and distributional clearance as well, weight. And I have my random effects. So I simulate from this model, and then I have a profile at reference. So here I didn't vary. Weight, albumin, sex are all at reference. It's only the BSV that I'm illustrating. So once I have this super rich profile, I can compute AUC, Cmax, etc., any statistic I want, and then I standardize. So now I have everything lined at one, and then I can understand, okay, the BSV at reference, it's narrower for Cmax and it's wider at Clast, and it's the middle for AUC. So that's how I generate PK parameter from PK profile, and I compute interval at reference. So very quickly, when we have BSV, how do I illustrate my BSV in a force plot context? So what I do from my simulation, I try to compute. So that's a distribution, say, normalized. Think of it as it can be clearance, or we can transform it into AUC. But what I'm interested in is to know where are my 50% of patient or 90% of patient. So to do so, I compute in my package, I use median and percentile to say, okay, where is my patient? And basically I summarize this distribution of BSV having a separate facet called BSV, and 50% of patients are between 0.88 to 1.14, for example, and 90% would be covered from this point to this point. And I contrast with the covariate effect. There is an example later. I know, like, especially in Bayesian statistics, we use high density interval, but yeah, and as pharmacometrician, I mostly use median and percentile to illustrate my BSVs. So after I define my mrgsolve model, I define this combination of covariates. That's a function, a very nice function in the package called expand model frame, written by colleague Benjamin Rich. So what it does, it varies one covariate at a time. So weight is varied while albumin and sex are being held fixed. So that's a weight effect, while albumin effect, I vary albumin while keeping weight and sex constant, and so on and so forth. So to illustrate, okay, I simulate this 8 individual, and you see what is the impact of weight on the PK profile when only weight is changing, when only albumin or only sex is changing. So now I simulated only one profile, but I want to incorporate the uncertainty. Like I want to simulate maybe 1,000 profile and compute interval. So that's how I illustrate. You can use variance covariance as mentioned, or bootstrap, or SIR. So now instead of having only one value of Ka, clearance volume, you have maybe 1,000 that came from your uncertain distribution. And I plug this into the simulation by selecting one row of this group of parameters for each replicate. So I also zero the omegas. It's a cool feature of mrgsolve where you can easily turn off the BSV. And I repeat my simulation, and then I compute these summaries. I also, like, you can easily parallelize this simulation using for each or mrg parallel, mrg sim parallel, sorry. But I don't use parallelization in my vignettes because sometimes they crash on different platforms and CRAN would complain. But yeah, I can share examples where we use parallelization. They are quite straightforward. So we simulate, we compute parameters and then intervals, and that's BSV that I showed you here. So here I'm showing relative to reference, what is the BSV impact on reference, and we can clearly see here that weight has a largest effect. So on purpose, I put the largest effect covariate on top, then it's ordered by like the strengths of covariates. So largest on top, second, etc. So here we can see weight has the largest impact. Albumin is within clinical insignificance limit. Sex is or moderate or small effect. And as compared to BSV, whereas 50% of my patient and so on. So here I'm showing BSV only at reference, but if you want to think about range of predicted exposure, you can imagine that, okay, each point will have a BSV around it. But here I'm isolating the covariate effect. I'm not interested to see the range of possible exposure. I'm trying to see the contribution, relative contribution of each covariate. So this first vignette will show you how you can easily change like the looks. It's again pure ggplot. You can have any theme. So here, same plot, different visuals. You can have multiple parameter faceted, like split in columns, or all shown in like color by and shape by. So you have Cmax still as shown head to head. So it gives you tons of option, and you can do also so. So that's a summary figure from the paper. Just a recap that, okay, we simulate first one profile, we add uncertainty, we compute AUC, Cmax, whatever PK summary you want. As a pharmacometrician, I like the distribution, but these tend to be hard to interpret by clinical folks. So we prefer to illustrate using point interval. So sometimes like we call it forest plot. Some colleagues would complain, oh, forest plot are specific to meta-analysis. You can't call it forest plot, but you hope you understand me. It's just point interval shown in the forest plot like format with numerical table on the side. So here was a univariate case. So how can we jump or augment this into a multivariate / correlated covariate type of simulation? So the only difference would be, instead of varying one covariate at a time, you plug into your simulation a distribution of covariates. So here, in my second vignette, I don't turn off BSV. I include covariate distribution. And then I show the effect. And I will blow this forest plot in the next, so exactly same from the paper and vignette. So now, because we are simulating using correlated covariates, these splits are no longer pure effect. Like it's not just the weight effect. It is a joint effect of all covariate, but split or looked at from the weight angle. So that's, I'm splitting my whole population into quartile of weight. So I can see the first quartile, Q1, Q2, Q3, Q4. And as weight is increasing, AUC is decreasing. While when I look at male, female, okay, that's a split. We can appreciate that, okay, female would have a larger AUC, maybe because of like also the weight being lighter, but yeah, albumin has a lesser impact than weight. This is our joint effect split by percentile of interest, if you want. And here is just illustrating that you have the option to show the table below or on the side. You have multiple options. But yeah, it's important also whenever you do any simulation to explain what it is in your text. So you have an argument to write whatever you want in the legend. It's super easy. It's one argument. You write any text you want, and boom, you have it. So it's joint effect, etc. Covariate distribution, uncertainty, and BSV. Yeah, so we can no longer show effect at one particular value of covariate, rather it's covariate splits. And here it is joint effect, so we cannot isolate the effect, but still valuable and important to look at the data from that angle. So same type of approach. Also, I have a pediatric applications. The only difference, I show you how you can simulate correlated weight and age using CDC LMS values. And I also illustrate that maybe you don't want forest plot. You want to illustrate AUC versus age and weight. So I try to show you as many examples as I can, so you see whatever is best for your particular application. So that's also another case of correlated covariate, multivariate. And for sake of time, I won't be covering, like I have a PKPD vignette and even an exposure response logistic model, but I show you how you can simulate an mrgsolve and how you can compute the effect. So those interested can have a look. Over the years, people have used coveffectsplot for different applications and showing covariate. For example, here you can contrast the impact when you have a univariate statistical model. So you are testing a separate model for each predictor versus a multivariate one or multivariable one more correctly. So that's one potential application. And last ACOP talk, I had a stand joint model, and I was comparing I was interested to compare the effect of Moser diastolic pressure across models. So here I have model where I only have this, then I add more predictors. It's just to illustrate that the application can be wider than just illustrate the covariate effect. It's super easy to show point interval with a numerical table using this package. And that's another example where I got a Gompertz model. I show the effect on the curve, but here I chose, okay, I'm showing the effect of treatment on parameter. So it's a 4-parameter Gompertz model. And then, okay, maybe looking at the effect on alpha, beta, gamma offset can be interesting, but I can make more sense of it when I look at the impact on the curve. So that's also just a message here that don't forget to also show the impact in multiple angle, multiple ways. So it's good to see the effect on parameter, but also on the curve. It's very interesting. So I hope by now I have shown you that covariate effects plot are useful to communicate pharmacometrics model. Current technologies like C++ based mrgsolve simulation and R enable you to do this intensive simulation in a very reasonable time frame, like seconds to minutes. Many times I can live simulate scenario with client while on a call because super fast. So the coveffectsplot package is fitting software agnostic, and that's on purpose. You can bring in your model from any fitting software, non-mem, Monolix, Phoenix, and LMXR. Just bring it and simulate an R. It's 100% free and open source. And you have tons of examples in the CPT PSP tutorial. And mainly I have vignettes that illustrate 2 types of workflows. The univariate, where we vary one covariate at a time, and multivariate, where we plug in a distribution of covariates. So multiple covariates are varied at the same time. On purpose, I don't have automatic simulation or conversions. There's other packages that can help with that. I don't have automatic summarization. It's a few lines of code, show you how you can group, how you can use data.table, so you can do it on your own. And please feel free to submit feature request improvement or documentation improvement. If you'd like, say, to include an example with RxODE or any other application, please reach out on GitHub. Thanks. And now ready to answer any of your questions.
Thank you, Samara. That was really nice. I think this is really nicely presented, and these kinds of plots I think are something that are really essential to sharing the results of our work. So we have a number of questions online. So if anyone has a question they'd like to ask, please use the Q&A button in Zoom to add your question there. Just in the meantime, I just did want to comment that we are recording this webinar. If you want to come back to it later, it will be posted on the ISOP YouTube channel, and it will also be linked from the SXP webpage, and I will post a link to that in the chat here. Okay, so having said that, let's take a look at the question. So Samara, there's a question, is it documented somewhere how the data should be structured in order to generate forest plots with this package? I know you talked a little bit.
Yeah, of course. Yeah, so I'm trying to exit full screen. So we have it in the paper and in the documentation. So basically, early on, I show one, just getting to. So yeah, it is documented. So basically, we tell you exactly what the columns should be named and how they should be provided. So and we give tons of example, and the vignette will illustrate how you can generate the data in a compatible way. And let me check this. Yeah. And in the README of the package is illustrated. Even in the Shiny app, when you load the app, it has a help tab that explain. It really has the same explanation here. So I hope this gives options to document well the requirement for the data.
Great, thank you. So there actually are a number of questions related to generating the simulated data. So someone's asking, can we use simulated data exposure data from non-mem output directly? So you mentioned that you use ARP you can use some ARP packages to simulate this data. Is it possible to use the output directly from non-mem as well?
Yeah, well, of course you can simulate using non-mem and then bring your simulated. Well, it depends. So did you simulate profile in non-mem and compute AUCs and Cmax in R? That's possible. It's also possible to do all the computation in non-mem, like you integrate and you compute AUC. So, and then you bring in exposure really to R, and then you compute the interval. So the workflow is structured in a way it is stepwise and modular. So there's nothing preventing you, okay, to skip some steps or to use a different methodology for some steps. Okay, you don't want mrgsolve, I simulate in non-mem. And then I bring to R and continue my workflow. So that's totally possible. No problem at all. Tim, are you reading this question or?
Yes, I am.
Yeah. Okay, great.
So we are almost coming up to the end of the hour. There are a number of questions. Perhaps I can ask the attendees to follow up with you later if needed. I think we have time for one or two more. There's a question, does the R tool address the clinical relevance of covariates?
Yeah, well, so basically to answer clinical relevance, so basically I have this area here where it is clinically relevant, but okay, how do I define? So these are the bioequivalent limits, 0.8 to 1.25. But to really answer this question, you need to look at the efficacy and safety of the drug. So you might have a different therapeutic window. And here you might want to show the AUC interval not standardized because you have a particular like therapeutic window in terms of raw AUCs. So that's all possible. So that's why here the function itself lets you define any limits you want for your like clinically relevant limit. But yeah, that's a clinical decision or drug development team decision. So to determine this, it's a team effort, clinical pharmacologist, statistician, pharmacometrician. And once you have your answer, the package will just illustrate, okay, I know where is my limits and I can show it on the graph. The package itself won't tell you what are the clinically relevant limits. It will tell you the effect, and then depending on your efficacy and safety information, it might be relevant or not.
Right. Right. Well, that brings us to the end of the hour. So I'd like to take this opportunity again to thank you, Somer, for a really nice presentation. Thanks to our attendees for joining. Again, the video will be posted live to the YouTube page and posted on our SXP website. We'll also have the slides posted there and links to Somer's code in a GitHub repo as well. All right. Thank you very much.
Right. Thanks, everyone. And please reach out for all the questions that we couldn't address today. Thanks a lot.
Thank you so much.
Thank you.
Thanks. Take care.